Jumping beats. Here we go. In this video, we're going to talk about a really important differentiation technique, which, as you can see, is called implicit differentiation. So, what is this implicit differentiation? Let's take a look. All right, first of all, we have to figure out what this word implicit means. Now, thus far, throughout all these videos, what we've been doing is really focusing on what's called explicitly defined functions and then differentiating them. So when you have a relation, remember, a relation is just a collection of ordered pairs, right? But if you have a special type of relation in which you can write y as a specific function of x and all the good things happen, like, you know, every single input has exactly one output. It passes the vertical line test and whatnot. This is what we call an explicitly defined function, commonly referred to as just a function, right? So that's what we've been focusing on so far, and we've come up with, of course, a variety of rules. But just because I don't have an explicitly defined function doesn't mean I can't find the slope of the corresponding curve. And that's really what we want to get into. So, you know, just for example, some examples of explicitly defined functions, right? Y is cosine x. Y is equal to square root of x plus 1. Y is this polynomial x cubed plus 4x squared plus 2x plus 1. There's endless possibilities, right? But these are all examples of explicitly defined functions, because when I plug in a single value of the input x, I get back a single output value for the output y, right? But what about an implicitly defined relation? So again, collection of ordered pairs here, relation, is just a relation in which the relationship between the two variables, say x and y, cannot be expressed as a single explicitly defined function. So we won't be able to isolate the y, for instance, or maybe we can isolate the y, the output, but there's something in the formula that's giving us multiple output values for single input values, right? So a relation, again, a collection of ordered pairs, it has a graph. And so the only difference is that this graph is not necessarily going to pass the vertical line test, but the graph is going to be some type of curve. And assuming that the slope is defined, we should be able to find the slope of the curve at whatever point we like. That's why we talk about this video. So we're going to focus on this equation right here in this video. X squared plus y squared is 9. And of course, that is just a circle that is centered at the origin that has a radius of 3. So here's our circle, right? Clearly, it's not an explicitly defined function because at pretty much every single value of the input x, there's multiple outputs, right? It quote unquote fails the vertical line test, for instance, right? So you say, well, if I just pick an x, like right there, some x, what slope are we really talking about? Well, we can go and find the slope like right there, right? We could talk about that slope. But unless we know what's up with the y value, we won't know which one to specifically find, right? Here's another slope right down there. And so you think this is a nice and smooth curve, and we should be able to find the slope of it at any given point that we'd like. And so that's what we're going to focus on in this video, is how to approach a situation like this and why this method of what we're going to call implicit differentiation is going to be a nice tool to allow us to do exactly what we're asked to do. So let's keep going. All right. Now that formula that we have, x squared plus y squared is equal to 9 right here, we could solve it for the output variable y, right? If I just subtract x squared on both sides, I get y squared is 9 minus x squared. And then rooting both sides of this equation gives y is equal to plus or minus root of 9 minus x squared. So as we can see by the plus or minus, right, that's all consistent with the graph, is that for most values of x, when I plug in an x that defines this situation, I'm going to have both a positive root and a negative root of the 9 minus x squared, right? So one thing we could do is actually turn this implicitly defined situation into two different explicitly defined situations. So using the plus and minus of the root that we see right above. And thus we can kind of think of, okay, really this implicit relation is the combination of both, say, y1 equal to the positive root of 9 minus x squared, and y2 is the negative root of 9 minus x squared. You combine those together, we get the entire circle of radius 3 centered at the origin. But here we have two specific functions that are actually both explicitly defined. And so that's what this picture shows right here. It's the same circle, except you see the blue part, the top, that top semicircle, that's the function y1 is equal to the positive root of 9 minus x squared, whereas the semicircle that is below the x-axis is the other function, y2 is negative root of 9 minus x squared. So what we could do is we could find the slope of the tangent line at a point, whatever this point is, x comma y, assuming it's on the circle above, by finding the derivatives of each of the explicitly defined functions y1 and y2 individually. And then once we know a point on the graph of the relation, we could say, oh, it's either on y1 or y2, and then go find the slope from there. So we could do that, and we're going to look at that right now. So if I go ahead and differentiate y1, so y1 here is the root of 9 minus x squared, the positive root. Now remember, previously established results is that the derivative with respect to x of root x is equal to 1 over 2 root x. That's going all the way back to the definition of the derivative. We saw that there. So keep that in mind, because right here I'm differentiating this function. I got to use the chain rule. So what do we get? Well, the derivative of the inner function 9 minus x squared is a negative 2x on top, and then divided by, right, 2 times the root of the inner function, which is 9 minus x squared, giving us the result negative quotient x divided by square root 9 minus x squared. So there's the derivative of y1 with respect to x. And in fact, if I do the same thing for y2, I get basically the exact same thing, right? Except the only difference is there's a minus sign in front for that function in front of the root. And so the negatives here turn to a positive, and we get this formula right here. Positive x divided by square root 9 minus x squared. So there we go. We have each individual derivative for both the top semicircle and the bottom semicircle. Now, let's consider a couple points that are both on this implicit curve. These 2 points right here, 3 root 3 over 2, comma 3 halves, and 3 root 3 over 2, comma negative 3 halves. Notice that if you plug those x's and y's back into the relation, it would satisfy the relation. X squared plus y squared is 9. So they're definitely on the graph of this circle. And in particular, the first order pair, which is in quadrant 1, right? That's a part of the top semicircle, y1 as we were calling it. Whereas the second ordered pair, 3 root 3 over 2, comma negative 3 halves, that belongs to the bottom semicircle. So it's really the same x value, right? But then you have the positive output and the negative output for these corresponding ordered pairs. So since we got the derivatives now of each individual function, let's go ahead and find the slopes. So like we said, the first ordered pair, which is in quadrant 1, belongs to the function y1 here. And so I'm just going to evaluate my derivative of y1 with respect to x at that input value, x is equal to 3 root 3 over 2. So it's kind of a little bit of a mess, right? So remember our formula, here was negative x divided by root 9 minus x squared. So there you go. I'm just putting the negative out in front. I'm replacing my x with 3 root 3 over 2 in the numerator and inside the root. And so cleaning this up a little bit, right, this 2 can come down here just by simple arithmetic. Square the 3 root 3 over 2, I get 27 fourths. 9 minus 27 fourths is the same as 36 fourths minus 27 fourths. And that gives me the following result. Negative 3 root 3 divided by 2 times the root of 9 over 4. Root of 9 over 4 is 3 halves. These 2's cancel each other out. Then the 3's cancel each other out. And we are left with the slope at this particular value of x is the negative root 3. Exactly. And approximately that's negative 1.732. So you think about that circle, right? If we are in quadrant 1 and we are at this location, we should expect a negative slope. And it is negative. Now we have that other ordered pair. The only difference is that it's on the bottom semicircle. So I'm using literally the same x, right? It's just that the output there, remember, was a negative 3 over 2. So because the formula for y2 is actually the same exact thing as the formula for y1, it's just the negative of it, then my result is going to be exactly the same. And you can verify it by plugging in this value of x into the derivative of y2 with respect to x. And you'll just get the negation of the result we just found, which is negative root 3. So we get positive root 3, which is 1.732, approximately positive. And here's a picture depicting all that. So right where these points are on the graph, right, this x value right there is x is equal to 3 root 3 over 2. And thus, you see that the slope of the tangent line on the top semicircle, right, that thing had slope, let's call it m1 equal to negative root 3. And then the slope of the tangent line on the bottom semicircle at this value of x, that slope, call it m2, was equal to positive root 3. So you can see that this is a thing we can do, right? We can take implicit relations and chop them into individually explicitly defined functions and then go about our business that way, finding each derivative for each explicitly defined function and then plugging in the corresponding values that we're interested in to find a slope. Problem is, sometimes that's not a very efficient method. Consider this situation. Here is an equation, cosine of y plus sine of x is equal to 1/2. Now, what's the graph of that look like? Well, if you go and get some technology, this is just part of the graph at least. It goes on forever in many directions. So as we can see here, there are many pieces of the puzzle. This thing is much more of a nightmare to deal with using the previous method than the circle that we were looking at, right? We'd have to literally chop each one of these in half to get two, kind of, I don't know what shape you'd call that, almost like a semicircle, right, but not. And if you did that, that's already 12 different functions explicitly defined. So you want to go and find 12 derivatives just for this one graph. And in fact, if you keep plotting, right, you're going to get more and more of these, and just like infinitely many. So we can see that the method we just looked at is not really going to be an efficient method in general, and sometimes it's even impossible. And thus, that is why, at least in part, that we have this method that we're about to see, which is called the method of implicit differentiation. And so here we go. Given an equation with two variables in it, let's just keep the x's and y's like we've been using. Let's just say the equation looks like this, okay? So, what does that really mean? It just means on the left-hand side is some expression with x and y. And in fact, on the other side is another expression with x and y. So, one side might be a constant, or both sides might have some expressions with x's and y's in them, whatever, right? The fact is, what we're saying here is this is an equation with two variables in it, x and y. And one is considered to be the input variable, and the other is considered to be the output variable when we graph the relation in general. So given that situation, if we have really, right, a implicitly defined relation, then what we're going to do, the method here, is differentiate both sides of this equation with respect to the input variable. In this case, that's x. Now, the thing that we have to keep in mind here is that we are assuming that, at least in this case, that y is the dependent variable. And so one way or another, y depends on x. Now, when I write this right here, I'm not saying that y is explicitly defined in terms of x, because otherwise we'd be able to solve for it. We're just saying that y depends on x, right? You put in an x, we get a y back, right? And because we can't solve for y explicitly in terms of x, the formula is unknown. So it's just some arbitrary thing that is a relationship in the situation. And so because of this, we have to keep in mind that anytime we see a y within the process, it's really a chain rule, because the derivative of y with respect to x is, well, guess what? It's the derivative of y with respect to x. And so when we differentiate both sides with respect to x up here, right, this stuff, that means we're going to have some dy dx's floating around after that first step. And so what we do is we isolate the dy dx, was what we're after, right? That is the slope of the curve. And so we solve the equation for dy dx, and we'll get our slope. That's literally the process. Now, easier said than done, right? Let's just take a look at one to end the video. And in the next video, I'm going to look at, several more examples to get this down. Let's just use the one we were doing earlier, right? Here is an equation that is implicitly defined. X squared plus y squared was equal to 9. So you can kind of think of the left side here, right? Some expression involving x and y. And really the right-hand side is a constant here, but you can think of the right-hand side as another expression involving x and y. It just happens to be a constant. So what's the method say to do? It says differentiate both sides of the equation with respect to the input variable. Now, if no one says anything, you're just going to assume that the input variable is x. And you think, why can we do that? Why can we differentiate both sides of an equation? Well, this stuff equals that stuff. And so if those values are equal, then we should expect that their slopes are also equal to each other. Let's do that differentiation step. I'm going to differentiate the left-hand side, x squared plus y squared, with respect to x. And I'm also going to differentiate the right-hand side, just the constant 9, with respect to x. All right, now the right-hand side, pretty straightforward, right? Derivative of a constant is just 0. But the left-hand side is where we see we have to think a little more outside the box. Okay, derivative of x squared with respect to x. Well, that's just going to be, of course, power rule, a 2x. But now I want to focus on the derivative of y squared with respect to x. We'll leave that there for the time being. And all of this, like I said, is going to equal to 0. So you think off on the side, what is up, just off on the side here, with the derivative with respect to x of y squared? Remember, y depends on x some way or another, right? It's the dependent variable. And so what we should be thinking here is this is a derivative with respect to x of some expression where y depends on x being squared. And so we've seen that, right? That's the generalized power rule for chain rule, right? So it's chain rule with a power involved. And thus that should equal 2 times the function y, and then lower the power of 1, but then times the derivative with respect to x of that function y of x. Or if we prefer, we can just write it as 2y times dy dx. So that's what I was talking about earlier, is that anytime we're differentiating something with the output variable, we gotta apply the chain rule for that reason. And thus my equation on the left here becomes 2x plus 2y times dy dx is all equal to 0. And as you can see, we now have an equation involving the unknown, the slope dy dx, in which I will algebraically solve for by first subtracting 2x on both sides of this equation, giving me 2y dy dx is negative 2x. And then I'll divide both sides by 2y to get dy dx is negative x over y. Look how much cleaner that is. That's my slope at any given ordered pair. And in fact, it involves both x and y, as it should, because if I only knew x, I wouldn't know what the slope is, because I wouldn't know if I'm on the top semicircle or the bottom semicircle. So I got to know both x and y. So let's just check. So remember earlier, we had that ordered pair, 3 root 3 over 2, comma, positive 3 halves. We found that the slope was equal to negative root 3. Let's plug those x's and y's into this formula and see what we get. All right, so dy dx, now evaluated at this point, let's just call this point P so I don't have to write it again, evaluated at this ordered pair now is going to be equal to, plug it in. All right, negative x on top, negative 3 root 3 over 2, all divided by the y value, 3 halves. So what is this the same as saying? Negative 3 root 3 over 2 times a 2/3. 2's cancel, 3's cancel, negative root 3. Exactly what we had found earlier, but remember earlier how much algebra and arithmetic was involved, and we had to differentiate two different functions and all this stuff. And so that's just our first example of applying the process of implicit differentiation. And like I said, in the next video, we're going to look at least 3 more examples to really get the process down. As far as this video is concerned, though, that's it. And until the next video, you know it, it's Math and Beats, and I'm out.